Hello again, everyone. Okay, our plan now is to talk a little bit about generating sets, which slightly extend the idea of cyclic subgroups that we talked about in the last one. So we talked about the cyclic subgroup generated by a particular element of the group. We also have the concept of a group itself being cyclic. So let me say what that means, and then we'll talk a little bit more about generating sets and about some examples. So a group is cyclic if it is the cyclic subgroup generated by one of its own elements. So a group is cyclic if there's some element A in the group with the property that every element of the group can be obtained from composing A or its inverse with itself repeatedly some number of times. And of course, also the identity is there. So that's what a cyclic group is. It's basically a group with the property that it has some special element whereby every element of the whole group can be obtained from this one by just repeatedly composing that one or its inverse with itself. And of course, the identity element can be obtained by composing this element with its own inverse. So cyclic groups are really groups that are generated by a single element in that way. Every element of the whole group is a power, basically, of this particular one or its inverse. So an example, the group of integers under addition is an infinite cyclic group generated by the element 1. Okay. What that means is if we take the integer 1 and add 1 to itself, 1 plus 1 is 2, do it again, 1 plus 1 plus 1 is 3, 1 plus 1 plus 1 plus 1 plus 1 is 5, and so on. Every single positive integer can be obtained by adding 1 to itself some number of times. The inverse for 1 in the integers is minus 1 under addition. Every negative integer can be obtained by adding minus 1 to itself some number of times. And the zero element is the identity. It's also 1 plus minus 1. Okay, so 1, the number 1, generates the entire additive group of integers under addition. Every integer is either the identity element, 0, or it's 1 added to itself a number of times, or it's minus 1 added to itself a number of times. An alternative choice for generator there is minus 1. That does the same job, generates the full additive group of integers, but no other integer besides 1 or minus 1 will do it. Okay, if we take a natural number n, so take 7 or 20 or whatever natural number you like, the group of nth roots of unity in the group of non-zero complex numbers under multiplication is a cyclic group of order n, generated, for example, by the complex root of unity e to the power 2 pi I over n. Okay, that's the complex root of unity that has modulus 1, obviously, and has argument 2 pi over n. As you take the powers of that one, you get all the complex nth roots of unity. Okay, that's a second example. A third example, if you take the regular n-gon, the regular polygon with n sides, it has a group of rotational symmetries with n elements. All the rotations through 2 pi over n, or through any integer multiple of 2 pi over n, those are all rotational symmetries of this object, and all of them are generated by taking one through the smallest possible angle, 2 pi over n, and composing that one with itself. So again, it's a group of symmetries that can be obtained in which every element is really a power of a single one. And of course, an important point to note, and it relates to the challenge that's coming up at the end of this, is that, you know, if we take the regular pentagon, for example, rotate one step through 2 pi over 5, do that repeatedly, you get all the rotational symmetries. That may not be the only particular example of an element that does that job, but it certainly is one example. Okay, so those are 3 examples of cyclic groups that are familiar to us. One is the infinite cyclic group, integers under addition, and 2 other examples of cyclic groups, each with n elements that turn up in different contexts. One in the context of complex arithmetic of complex numbers, the other in the context of geometry of polygons. An observation, a remark, is that cyclic groups are always abelian, because in a cyclic group, if you take any 2 elements, they're both powers of the same thing, so they're going to commute with each other for that reason. Cyclic groups are always commutative. Their operation is always a commutative operation. So if you see a group that is not abelian, that has elements that don't commute with each other under the operation, then you know for sure that group cannot be cyclic. Okay, so another thing that I'll just remark on is, you know, we've seen there in the last slide that complex roots of unity form cyclic groups. The group of complex 10th roots of unity, for example, is a cyclic group. Groups of rotations, groups of integers. Another example is a group of integers modulo n under addition. So you kind of see cyclic groups of order n turning up in different places. From the abstract point of view, you could say that these groups are really all the same. They all just consist of a single element and its n powers. So you could think of them really as being sort of the same group, just turning up with different sort of manifestations in different contexts, in geometry, in algebra, whatever. So it's kind of typical practice to think of the cyclic group of order n, and just think of that as a sort of a thing with a single thing that turns up in different contexts. Generically, it's written as C subscript n, cyclic group of order n, infinite cyclic group like the integers under addition, written as C infinity. So we might think about the cyclic group of order n as having the generator x, and think of it as being generated by this element and write it with x angle brackets around it. So its elements then would consist of the identity element, x itself, x squared, x cubed, up as far as x to the n minus 1. We had that example in at the end of the last session about a matrix which had order 3. The cyclic group that it generated just had 3 elements. The matrix itself, its square, and its cube, which was the identity. Okay, we take it x to the power n as the identity element, and when you're multiplying elements, you just add their indices as though they were ordinary powers of ordinary things and reduce modulo n if you need to. So in this context, this is sort of the ultimate abstraction in group theory. You're thinking of some group with some generator x. You don't care what x is, what type of object it is. Sure, in some particular application, it might be a number, and another one, it might be a permutation or a polynomial or a matrix or whatever. But you're just thinking about x as being something that generates a cyclic group of order n. It has powers, x, x squared, x cubed. Its nth power is the identity element, and its multiplication table you can actually write down. It would look like this. So it's missing a row, sorry for that, but I'll correct it in the slides that are posted. It's got an identity element, identity. It's got x, x squared, x cubed. X to the 4th is the identity. So if you want to multiply x squared by x cubed, for example, you get x to the 5th. X to the 4th is the identity. So that's the same as x. And this is how its multiplication table looks. Okay, so yeah, that's just a remark that it's sort of useful sometimes to think about this cyclic group of order n as having this kind of abstract life and just being manifested in different contexts that might arise in particular applications. Okay, that's a cyclic group. So a cyclic group, again, is a group which is generated by a single element through all its powers. The starting point here was to take a particular element in a group and look at the cyclic subgroup that it would generate, which would consist of all the powers of that element and its inverse and the identity element. You could do the same trick for any subset of a group, not necessarily consisting of a single element. Suppose we have some group G, it has an operation, and we take any non-empty subset of the group. So for example, think of a subset with 2 elements maybe, or with 1 element. We've covered the case with 1 element, but think of a subset with 2 elements. Okay. So we can define the concept of the subgroup of the whole group generated by this element S. Okay. So if S has a single element, that's the cyclic subgroup generated by that element. But if S has 2 elements, let's say they're called X and Y, then we can say that any subgroup of G that includes both the elements X and Y would have to include anything that you can get by composing X with Y, or by composing X with X, or by composing X with the inverse of Y, and by doing all these things repeatedly. So anything that contains the element X and the element Y would also have to contain the element Y, 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 X. Those 4 compose with each other in that order. It would have to contain the element Y, Y, X inverse, Y inverse. Those 4 things compose with each other because it would have to contain the inverses of both X and Y, and it would have to be closed under the operation in G. So the concept that we applied to cyclic groups generated by a single element, we can also apply to define the concept of the subgroup generated by a pair of elements or by 3 elements or whatever. So if S is our subset of elements, then this subgroup generated by all of them would be denoted by S with angle brackets around it, consistently with the notation for cyclic groups. It would consist of all the elements that could be obtained by starting with the identity and the elements of S and their inverses and composing all those things in all possible ways. It might not be easy to figure out exactly what it is, but it exists in principle. And it's the smallest subgroup of G that contains all the elements in the set S. So a key definition here is that if you have a subset S with the property that the subgroup that it generates is the entire group, then you say that S is a generating set of G. Okay. So if S is cyclic, it would have a generating set consisting of a single element. If it's not cyclic, it won't have that property. If it's not abelian, it can't be cyclic. So it can't have a generating set consisting of just 1 element. But a question that people like to ask then is, well, if you don't have a generating set consisting of just 1 element, do you have them with just 2 elements? If not, do you have them with 3? What's the minimum number of elements that it takes to generate your group G? And of course, the answer to that might be you need infinitely many elements, or it might be, even for a very large group, for example, that you only need 2. So the question for a given group of how many elements you need minimally to generate it is a question that is of considerable interest in group theory, and there's a large body of literature and theory around that question. Some people call it the rank of the group. Here's an example, which I think is hopefully fairly accessible if we know about dihedral groups. So remember that D subscript 2n is the group of symmetries of the regular polygon with n sides. So here's a picture of an octagon. D16 would be the group of symmetries of this octagon. There are 8 reflections. One of the lines of reflection is shown here. There are 7 more, 3 more through midpoints of pairs of opposite sides, and 4 through pairs of diagonally opposite vertices. So there are 8 reflections. There are 8 rotations as well. What's shown here is just like 1/8 of the octagon. So a rotation through 2 pi over 8 would sort of move this point 1 step counterclockwise, and the same for all the others, and all the powers of that rotation are further rotations. So the assertion is that if we take the subset consisting of a rotation through 2 pi over n or 360 over n, so for the octagon it would be 1/8 of a full rotation, and the reflection t. So t is just any one of the reflections, so we can think of it as being the reflection of that vertical axis here for the octagon. The assertion is that those 2 elements, the rotation through 1 over n of a full turn, and any one of the n reflections, are enough to generate the entire dihedral group of 2n elements. And to see that, we can observe that, okay, if we take the rotation through 360 over n and start composing with that with itself repeatedly, that way we get all the rotations. If n is 8, then this is the rotation through 45 degrees. Compose it with itself, you get 1 through 90, then 135, and so on. By the time you've done it 8 times, you've got the rotation through 360 degrees. And in the process, you've picked up all of the 8 rotations. So certainly, from these 2 elements, by composing them with each other and with themselves, you can get all the rotations. And then the other observation is once you have all the rotations, you can compose each of those with this particular reflection t, and that will give you all of the 8 reflections. So by taking the rotation through sort of the smallest possible angle, I suppose, 360 over n, and by taking any one of the reflections, you can generate the full subgroup consisting of the rotations, and then by composing all of those in turn with the reflection, whichever one that you started with, you can get all the reflections as well. So the dihedral group of order 2n, the group of symmetries of the regular n-gon, is an example of a group that can be generated with 2 elements if they're suitably chosen. It can't be generated by any 2 elements, but it can be generated by a suitably chosen pair of 2 elements. And also it can't be generated by a single element. It's not cyclic because it's not abelian. Not all of its elements commute with each other. So we can say that 2 is the minimum number of elements needed to generate D2n, and we can demonstrate a pair of 2 elements that do that trick, that do that job. Because that's the concept of a generating set. We'll come back to it from time to time. It's an important thing in group theory, certainly. We won't be using it an awful lot more in our course, but it's a very good concept to have, and there are a few questions in the current homework that involve investigating generating sets for different groups. Certainly the distinction between sets that can be generated by a finite number of elements and the ones that can't is an important thing in group theory. And people study finitely generated sets. Those are the finitely generated groups. Those are groups that have finite generating sets. Some groups don't. And an example of a group that doesn't have a finite generating set is the group of rational numbers under addition. And that's a nice thing to think about when you have a chance. Okay, here's our challenge for this one. So this challenge is actually about cyclic groups. So if we let Cn be the cyclic group with n elements, and you can think of that either abstractly, as we had the table there for C4, or you can think of it, for example, as the group of complex nth roots of unity under multiplication of complex numbers, or you can think of it as the group of rotations or a regular n-gon, whatever you prefer, or if you want, the group of integers modulo n under addition. Those are all sort of relatively concrete manifestations of the cyclic group with n elements. So the question is, the definition of a cyclic group, by definition, we say a group is cyclic if there's some element that generates it through all its powers. So the problem here is to figure out, for Cn, for a given n, so think about n being 10 or 20 or 12 or whatever your favorite natural number is, how many of the distinct elements of that group generated as a cyclic group? Okay. The answer is different for different n's. So the question really is, can you explain how the answer to that question depends on n? There's a formula for it in terms of n. It's something that you're probably familiar with, maybe from first year if you did MA 180, but maybe it's not something you think about all the time, and maybe not in this context. So can you describe how the number of distinct elements of a cyclic group of order n that generate the group, how that depends on n. Okay. Thank you very much, everybody. See you later in the week. Thanks a lot. Good luck.